you've had time to look at that. And let me ask you, okay, we are starting to be able to do this. We've found exoplanets, and we're starting to be able, there's one that has like diamond rain, which is really weird until you think about diamond being the extreme end of heat capacity, so it's very stable. And if it forms, if you form it, it's not going to unform. And you have conditions where you would actually have a lot of diamond. So maybe diamond, don't buy stock in a diamond company. Well, that might be a leap. But if we can detect things like diamond raining on a planet, we could detect other gases important to life. And so you have a telescope, and you want to look at these planets. If you could, what would you look for? You know a little bit about the story, especially after reading half the book, right? So what would you look for? Yeah, that's oxygen is what everyone says first because, over time. But the thing is, there are geological processes that can produce oxygen. And it looks like some of that's going on Mars. But we see some other things as well. And I heard carbon. What form of carbon? Because carbon, just carbon, would be like diamond. So, Susie, was that you? So, could be CO2? Or what else? Okay. Could be like benzene or something like that. I mean, remember that benzene, we had that heat of formation, and it was more unstable than the others. So we probably wouldn't see a huge amount of benzene, although it would be really cool to find it. But we'd probably see alkanes, like C2H6 and things like that. And that's what we do see on Titan. So we can look at Titan, and we can sort of get a measure of what these are going to be. If you can see a lot of C2H6, what are you going to see that's even simpler? CH4. So methane, carbon dioxide are big things to look for. But methane, remember the whole Titan story is, what's surprising about Titan is what's missing. That you're looking for hydrogen, but it's not there. And we don't know why, if it's not there because something's eating it or because it's reacting passively with something. So hydrogen is something we can look for, methane. These are all simple molecules, and most gases are simple molecules. Carbon dioxide is, in a sense, the most complex gas we're going to look for. And that's what we can really look for. We can't really look for liquids or solids as much as we can do. Gases light will shine through them, so it's like a spectrometer for it. And have you heard about how there's mysterious methane on Mars? And it is related to the seasons. So that sounds like life, right? But also, why do the seasons happen? Because of geology. The Earth is tilted. Mars is tilted a little bit. So you do have geological explanations for the methane as well. Here it is, and it's not happening all over the place either. But also, rocks aren't the same affluent. So we're recreating the astrobiology debates that they're having right now. Here are the possible things that can produce methane. You can have the sun, UV light, producing methane from surface organics. You can have microbes producing it from the solid. Or you can have olivine reacting with water. And we know that there was water on Mars before it got to be bone dry. They actually call it the Noachian period, when there was a lot of water, but because N-O-A-H, I'm not sure if I'm saying it right, but it's N-O-A-H, Ichen, okay? And that is like when Mars was flooded. And so there clearly was a time like that. And so you can have this production, and you can also have the production of carbon dioxide. So realize that these things, even oxygen, can be produced geologically. And so it's not like we're going to be able to look at one thing and say this means that it's probably life there. But we need to look at more than one thing. And if that's the reason, we need to think about the fluxes and reactions between these different things. And that's exactly what this paper is about right here. The one thing we know about life is that it is not at equilibrium with its environment. So if there's a lot of life, enough life to influence the atmosphere of a planet, then the atmosphere itself will be at disequilibrium. There's more than one way to have disequilibrium. If you have any kind of reaction that takes you away from equilibrium, a geological reaction can also take you away from disequilibrium. But it probably won't be disequilibrium for a sustained amount of time by itself, okay? So this is looking for these signatures in disequilibrium, looking at more than one thing. And there's two things that we look here. They're thinking right here about, they go for the answer everyone says. We want to look for oxygen on other planets. And they're actually saying that oxygen by itself doesn't say as much as oxygen that is present with nitrogen and liquid water. All three of these things detected would be a biosignature. But what about before oxygen? We know that there was a time, it's the whole thing about what William said. What do we look for then? Do we look for methane or do we look for CO2? Actually, the answer is both. So again, you have N2 and liquid water. Those are both important for life, and those are biosignatures. But you look for not just one or the other, but you look for the presence of both, and that is a disequilibrium. Because one or the other could react and produce a lot of one side of things. But when you have both around, at equilibrium, one of them is going to be gone. It's like, the Highlander. Does anybody know that? The tagline for that, there can be only one. It's a really terrible old movie about like sword fighting and things like that. I have a lot, but there can be only one of the carbon at equilibrium under normal geochemical fluxes. And I love this title, this graph, because they show over Earth natural history. Oxygen in the air went up. That's the blue bars are the bounds of oxygen. And the main thing that everything is that I'd have to retract my writing if it came out against this, if this slope no longer went up. But that slope is going up over history, and we know that we have oxygen now, but for 9/10 of our history, we didn't have oxygen, and yet we did have life and even photosynthesis. Now, the thing about oxygen provides energy. Don't overlook the y-axis here. The available Gibbs energy. So that's a weird kind of way, but you don't recognize the symbol, but you recognize these units. The joules per mole of the atmosphere, the amount of the atmosphere that is available to do work. And that's what it talks about that as oxygen increases, that increases. And so they're talking about looking back here when there wasn't as much oxygen, there wasn't as much available energy, because the other things don't give you as much energy. And so they talk about cases like this. If you have this state and you have nothing else going on but normal geological processes, it will not stay there. It will turn into this state at equilibrium, and you can calculate this state because it will minimize its Gibbs energy. This is the minimum state, and you can get this by running all the reactions together. You can calculate the kilojoules per mole of a system. Your system can be the atmosphere of an entire planet. So as long as you haven't left anything out of your calculations, you can actually do this with physical chemistry. And you can say, if I had a lot of oxygen in the air, it would react and it would produce nitrates and protons and H2O in the atmosphere. So this is what they were doing. They were looking at the free energy and what is a concentration that's big enough to be detected with a telescope. What chemicals do we look for? That if we see this, that's really weird because that means the planet is not at equilibrium. Okay. Memorize this for the test? No. But if I want to show you this, because look at all the things that you actually do recognize from Atkins. What they're doing is they're adding up a bunch of delta G reactions. They're adding up a bunch of nRT, natural log of ratios between initial conditions and final conditions. And they're using activities. They're even using the chemical potential. This is the activity symbol. I think you can see the chemical potential. And actually, they don't do it that way. So anyways, but they're just adding up stuff. It doesn't really matter exactly what they're doing, but I want you to recognize this is how you calculate the free energy of an atmosphere, using the stuff that you have learned. And so they come up with this, they run all the delta G's, and they throw everything together in their computer, and they calculate how it all works out. And they see is if you start off with an initial system that looks like the blue bars, at equilibrium, you'll have a system that looks like the green bars. And so what you'll see here is if you start out with a lot of oxygen, you will have less oxygen at equilibrium. So yes, look for oxygen. If you want to see a system at disequilibrium, if you see a lot of oxygen and you see these other things as well, that's unusual. That would not be at equilibrium. It's not a green bar, it's a blue bar. Also, you could look for methane. In an oxygen-rich atmosphere, the methane should naturally react. But of course, if you looked at our atmosphere, you wouldn't see much methane, right? Because it reacts and it gets eaten. You're looking for the absence of things more than the presence of things. The presence of a combination of things, perhaps. So this is the time when you have oxygen. What about when you don't have oxygen, okay, in the atmosphere? What happens then to the green and blue bars? Well, right there, your initial mix, if your initial mix has both oxidized and reduced forms of carbon, at equilibrium, you'll only see methane. I think there are other conditions where at equilibrium, you'll end up only seeing CO or CO2. For complicated reasons, they don't show CO2 on this graph because it's involved with dissolving in seawater, and they're always looking at atmosphere. But all that is to say, if you see both blue bars, that is not equilibrium. That's initial conditions. And that means there's something keeping it away from equilibrium. That something could be sunlight, by the way, shining on Mars, but that can only produce so much chemical. So if you see a lot of it, then you get more and more suspicious. It might be that the discovery of life on other planets is going to be more of a dawning realization from clues like this rather than a signal saying, hi, we're here, because we haven't received a signal like that yet. That's really weird. Okay. So I just want to point out that you're looking for a disequilibrium. On early Earth, it would be CH4CO2 disequilibrium that would be really indicative. And the absence of CO, not because the CO would poison life, but because back then the CO would be used for food. If you think about it, CO is like O2. And you could break the bond and use it for energy. And that's exactly what they think would happen. Okay, so that is, I have one more paper that I want to talk about. And it's the question of why does burning anything always release energy? So I gave this to you before. I want to give you a really quick overview of it. And I want to ask you to look over it, think about it. It will help you on all the problems on the test. But this is another thing that I will give you a problem that you can choose. Because this is exactly what we've been doing. So the question is, why is fire always hot? If you look at the double bond in O2, it's actually much weaker than a CC double bond or an NN double bond if you have other things stuck to the end. The O2 is actually a weak double bond. And so that's actually good. That's for the reason, and this is why it's important to understand what's going on when you're talking about energy and bonding. It's not that the O2, you break it open and you get a lot of energy just by itself. You get a lot of energy from the difference between reactants and products. So the reactant has a weak double bond, and you form a strong double bond, or stronger bonds, ratio-wise. If you look it up, the OH single bond, two OH single bonds are stronger. They're bond formation energies. And remember, bond formation energies, two atoms come together, heat comes out. More heat comes out from bringing two OHs together than from bringing two O's together. Okay? So this is the basis on which things work. But why is it always that way? Why can't we find a compound for which it doesn't? If we're talking about a difference between reactants and products, why are all the products down here relative to reactants? Why isn't there any product that's like up here? For other substances, by the way, with similarly weak bonds, we can usually find a case where you have an endothermic reaction. All combustion reactions, however, are exothermic. And so that requires some explaining to do. All right, so you can have here is a reaction of formation of methane, for example. And when you form the CH4 bonds, it gives off, 4 times the CH bond formation in this case, and it would be, it gives off 74.8 kilojoules per mole. However, when we do the exact same thing, but we throw oxygen into the mix, all of a sudden, the heat for this reaction, this is a combustion reaction rather than a formation reaction, but realize the only difference is we add oxygen. All of a sudden, we're like 10 times, more than 10 times as much energy given off. What we've done is we've added a weak double bond to it. So that's pretty amazing. It means that these things are really stable that it makes. And that was also on a graph that we showed at the end of last class. Okay. So you can look at these things and you can compare these things. This is glycolysis in the presence of, or this is not just glycolysis, it's complete combustion of glucose in the presence of oxygen. Gives you 3,000 kilojoules. If you do the exact same reaction in the presence of hydrogen, 1/4 as much energy. So and this is one of the reasons why I'm so assured when I say that there's no complex life on Titan, because there's just not energy for it. And that's why I'm skeptical about Europa. Hydrothermal events only give you so many joules. Compare that to this. And, if I gave you a number of points on your test for which reaction you chose, everyone would choose this reaction, right? You want four times more points. And you'd go for that. And life has the same kind of thing. It chooses the reaction that will be more energetic. So, how do we do this? But there is a typo here. That's one of the reasons why I give this to you, because you can't just take the paper. You have to listen to me, okay? Actually, you can catch the typo. This is the delta H of combustion. Look at that equation and tell me what's wrong with it. Yep, they screwed that up. So even physical chemists can get the products and reactants mistaken. It's possible that they justify it by using the heats of combustion in a positive way rather than a negative way, but they don't make that clear. And so I'm going to sort of say, I'm going to assume that they missed that. And by the way, heats of combustion, negative, okay, not positive. So there's definitely something going on there that's not right, okay? Now they have these figures, and these look really complicated unless you've had physical chemistry, in which case you can actually see the energy levels that they're doing there. So what they're doing is they're showing the energy levels of the different bonds, the reactants going to the products, and they have throwing oxygen into the mix. So remember that the oxygen bond is being broken, okay? And breaking the bond is actually going to be a positive number here, okay? But they're talking about it takes energy. Oh, well, I'm sorry. Breaking the bond will be a positive energy out, right? So forming the bond will be a positive energy out. Breaking the bond requires energy. That's a negative. And so that's why you have the -2 there. You have to put energy in to break the oxygen bonds, and then you reform them in CO2 and H2O. And this is why they say oxygen is weaker, has a weaker double bond, because you're forming double bonds here to carbon, but they're 804 kilojoules divided by 2, whereas here you have the oxygen double bonds are way up here. And you also have to account for the fact that you're making multiple products, so let the math take you where it will. But these numbers are big, and you're losing this number and you're going down to this number. The difference between these two is the energy that you get. So they're showing that you're going up, you're starting at this level, and you go up to 0, in a sense, to make the free atoms, and then you put the free atoms back together, and you go down to this level. That's what they're trying to show you here. So if you take methane and you combust it, you end up with -890, and if you take water and you form it, you come out with -1143. Those numbers are related to this number, but these have the oxygen number mixed in. When you're doing the math, you're doing all this. And this is just trying to show you something with a graph that looks kind of complicated, but if you do the math enough to where you get the homework math in your head, I suggest doing it that way rather than thinking about the graphs too much. Okay? But this is what they're trying to show. They're trying to show that you break two bonds that are up here, you break these carbon-hydrogen bonds, and you form these bonds. These bonds, the product levels of bonds, are more stable overall than the reactant levels of bonds. They're up here. You're trading this level for that level. And so the difference between that is the energy that it gives off. Therefore, delta H is negative, and it's producing energy. Losing bonds to carbon, right here, you're losing the bonds to carbon if you're burning glucose. You're breaking these bonds and you're forming double bonds. And it's proportional to the amount of oxygen in reaction. So it doesn't really matter that much what the configuration of CC, CO, CH, and OH bonds are that you're breaking. The really thing that gives you the most energy is the fact that you're breaking these weak oxygen bonds, which are way up here, and you're gaining these strong oxygen bonds, which are way down here. The biggest difference on this graph is the red line, not the blue line, which is hydrogen bonds, bonds to hydrogen, or the black line, which is bonds to carbon. So because the red line is bigger, that is why oxygen, whenever you're burning oxygen and combining it, you're going to have a huge contribution from that. And it drowns out the other ones because even if you're breaking fewer oxygen bonds, they're worth 3 times as much as the other bonds. Therefore, because oxygen is the constant in all combustion reactions, and it's always giving you an amount of energy that dwarfs everything else, you can't find a configuration of carbon and hydrogen bonds. You can't find a substance that has like super weak carbon and hydrogen bonds that are enough of those to overcome the large negative of oxygen. You just can't. And so that's why fire is always hot, because oxygen will always give you this red contribution. Again, this is the kind of thing that hopefully we make it clear to you as far as math reasoning rather than graph reasoning. I think that math reasoning is better for this, but you can't do that without going through a physical chemistry class and doing the homework, you know? There's one thing that they didn't forget that I want to encourage you not to forget. Remember the kinds of problems we had where you had to go back and calculate the heat of condensation? Because we're talking about going to water liquid as a product, but you're starting off with something that's not liquid. You know, you're technically, the heats of formation involve gases. So you have to account for the water coming together to make liquid. And so they said, okay, oxygen accounts for most of it, but actually you get the heat of condensation from H2O for most of these things as well. How are we sure that it's all about the oxygen and not about the heat of condensation? Well, they went and calculated it for each of these reactions and found that on average, yeah, you do get some heat of condensation contribution. But if you take a bunch of combustion reactions and see on average, the oxygen gives you 10 times more energy than the condensation of water. So there's no, again, you can't find some kind of thing where the condensation of water is giving you more energy than oxygen. They did 529 molecules that were combusted, probably in a calorimeter. And they basically found that there's a straight line between the heat of combustion and not any of the bonds other than the bond of oxygen and a 10% contribution from the condensation of water. So if you just know how many moles of carbon and hydrogen you have, it doesn't matter anything else. It doesn't, the number of bonds you're forming, not the nature of the bonds you're breaking, those don't matter. The number of bonds you're forming to make CO2 and H2O, that's what matters. And a little contribution from the H2O condensing. This is a really nice line for a lot of different things. And notice the similarity to the other paper that we gave out. Really nice line, a lot of different things. They actually had a way to predict the heat of combustion without knowing anything about the molecule other than the number of moles. And they said, how well does this predict? And in general, it predicts very, very well. If you just take the number of moles, and it works for having oxygen and nitrogen thrown into the mix as well. So our conclusion is, what makes fire hot is oxygen makes fire hot. and the particular chemical characteristics of oxygen swamp out everything else. That's why I'm comfortable saying that these conclusions are universal. And whenever I see a sci-fi show that has like systems running on other energies, that's nice, but I'd like to see the chemistry. And I'm skeptical that you can get enough chemistry. And don't ever watch a zombie movie with me, because I'm always like, they can't move that fast, you know? They don't have enough energy, you know? You have to break down a lot of carbs to do that. Not a lot of carbs in brains. But anyways, it is not the carbon, it's rather the oxygen that is energy rich. And to connect it to the book, oxygen is universal. And its characteristics in this respect are also universal. This actually is a cool thing for finding life on other planets, because it means we might be able to eat it. Okay, it might have some shapes that don't fit well with our shapes, but in general, the idea of combustion should be universal, and running on oxygen should be universal, so we should look for oxygen. And that is the data talk.